Now consider this example. The following key values are inserted into a B plus tree in which the order of the internal node is 3 and that of the leaf node is 2 in the sequence below. The order of the internal node is the maximum number of tree pointers in each node, and the order of the leaf node is the maximum number of data items that can be stored in it. The B plus tree is initially empty. The sequence is 10, 3, 6, 8, 4, 2, 1. The maximum number of times the leaf nodes would get split up as a result of these insertions. So we need to construct a B plus tree index with this insertion sequence. It is given the order of the internal node is 3, which is the maximum number of tree pointers which can be kept in the internal node. That is the maximum number of children an internal node can have. Then what will be the maximum number of keys that can be kept in the internal node? 1 less than it, which is 2. Now the order of the leaf node is the maximum number of data items that can be stored in it. It means the order of the leaf node is the maximum number of keys in it. Each key will be associated with its corresponding data record pointer. So what is the maximum number of keys that can be kept in the leaf node? It is also 2. Thus the maximum number of keys in the non-leaf and the leaf node is same 2. Now we have to find out the maximum number of times the leaf nodes would get split up as a result of this insertion. We have seen that while constructing the B plus tree, we can either make it left biased or right biased. Based on it, the number of splits required may vary. So we shall consider both the cases and see in which case the maximum number of leaf node split will be required. So this is the insertion sequence. In the beginning we have a single node, hence the root node itself is the leaf node. We inserted 10, then we inserted 3 along with its data record pointer before 10 to keep the sorted order. Now insertion of 6 will cause an overflow. Now the leaf node should split. So one leaf node split is already required, and in this case we will keep more items to the left and the maximum of the keys on the leaf nodes of the left subtree as the key which will guide the search. So 3 and 6 are kept on the left node, 10 is kept on the right node, and 6 is pushed to the parent level to guide the search. So we are keeping more items to the left, and the maximum of the keys on the leaf nodes of the left subtree is pushed to the parent level in order to guide the search. Next we should insert 8. 8 is greater than 6, 8 is less than 10, thus 10 should be pushed to the right and 8 should be placed here. Next we should insert 4. 4 is less than 6, greater than 3. Thus 4 should occupy a place between 3 and 6. There is no space in the node. This is a leaf node. Thus one more leaf node split is required. So currently the number of leaf node split is 2. We will keep more items to the left. Thus 3, 4 will occupy the left node, 6 will occupy the right node. The mid key 4 will be pushed up and 4 will occupy a place before 6. So this is the new B plus tree. So currently 2 leaf node splits are over. Next we should insert 2. 2 is less than 4. 2 should be inserted before 3. There is no more space in this node. Again one more leaf node split is needed. We will keep more items to the left. Thus 2, 3 will be placed on the left node. 4 will be placed on the right node. The key 3 will be pushed to the parent level. Now we can see when 3 is pushed to the parent level, it will cause an overflow at the parent level too. Hence this leaf node, non-leaf node should also be split. But we are after to find out the number of leaf node split, so we need not to consider this. Hence currently the number of leaf node split is 3. And how this non-leaf node will be split? 3 will occupy the left node, 6 will occupy the right node since even number of divisions. And 4 will be pushed to the parent level in order to guide the search. So this is the new B plus tree. The next one to insert is 1. Now 1 should be inserted before 2. Keeping more items to the left, 1, 2 will occupy the left node, 3 will occupy the right node, 2 will be pushed up, 3 will be pushed to the right, and 2 will be placed here. So one more leaf node split is required. So the total number of leaf node splits which is required in this case is 4. Now consider the other case. This time we will construct the B plus tree by keeping more items to the right, and we will choose the minimum of the keys on the leaf node of the right subtree as the one which will be pushed to the parent level in order to guide the search. So we will insert 10, then in the beginning there will be a single node, we will insert 10, then 3 will be inserted before 10, and insertion of 6 will cause an overflow. Thus the leaf node should be split up. So currently the number of leaf node split is 1. Now we will keep more items to the right. The 6 and 10 will be placed on the right node, 3 will be placed on the left node, and the minimum from the right subtree will be pushed to the parent level. In other words, we can say we show the 6 as the mid key which is pushed to the parent, and all the key data pointer pairs whose values are less than this key occupy the left node, and all the key data pointer pairs whose keys are greater than or equal to this key will occupy the right node. So currently one time leaf node has to be split. The next element to insert is 8. Insertion of 8 will also cause an overflow. Again leaf node should be split up. Thus 2 leaf node splits are required. We will keep more items to the right. 8 and 10 will occupy the right node, 6 will remain on the left node, and 8 will be pushed to the parent level. It can be placed after 6. After 8, 4 can be inserted. 4 can be placed after 3, no need of splits required. So currently the number of leaf node split is 2. Now we should insert 2. Insertion of 2 will cause an overflow here. Now leaf node should be split up. Thus currently the number of leaf node splits required is 3. Keeping more items to the right, 2 will be placed on the left node, 3, 4 will be placed on the right node, and 3 will be pushed to the parent level. And when the key 3 is pushed to the parent level, it will cause an overflow on this non-leaf node. Thus this non-leaf node should also be split up. But we have to calculate only the number of leaf node split up. So currently the number of leaf node split up is 3. Now how this non-leaf node will be split up? 6 will be pushed to the parent, 3 will occupy the left node, 8 will occupy the right node. So 6 is the minimum of the keys on the leaf nodes of the right subtree. Again 3 is the minimum of the keys on the leaf nodes of this right subtree, and so on. So finally 1 has to be inserted. 1 can be inserted before 2 can be pushed to the right, and 1 will be inserted here. No leaf node splits are required. So what the total number of leaf node splits required in this case? It is 3. We need not count the non-leaf node splits. And in the previous case, when we kept more items to the left, the maximum the number of leaf node splits required was 4. So what is the maximum number of leaf node splits required? It is 4, and it occurs when we keep more items to the left. So the answer is 4.